Loading. Yep, it works. So we are live now. Welcome to the second lecture on Introduction to Agent-Based Models. And today we are going to basically be talking about some terminology, some terms that we're going to use throughout the course. And later we are going to start understanding the interface of Netlogo, which is going to be the tool we're going to be working with during the course as well. So this is kind of the last bit of the last lecture. I didn't have time to finish the whole thing. So I just want to talk with you about some important aspects of agent-based models and why use agent-based models, why you have so many other tools like statistics and equation-based models and other stuff, and why is agent-based model like so interesting to use instead of other things. So we're going to talk about complexity, emergence, and other terminologies. So first things first, we're going to have to talk about complex systems to start, because, well, actually there is a very huge connection between agent-based models, complex systems, and even social networks nowadays. As a big chunk of the models, they're based on relationships and based on connections. So these areas, these fields are quite intertwined, and it's important to understand like what are we talking about when we talk about complex systems. And one of the main definitions we have in literature is that a system is considered complex when its parts interactions will result on an emergent outcome, which will also create a feedback loop affecting the individual decisions. It might be a bit like a complex to you at first, but we are going to unfold the terms here so you can understand what we're talking about. But first of all, I just want to say that complex systems, they're usually systems where you have so many variables, or where you have too much going on in such a way that the other methods, they just they won't support, they won't fit the complexity of the model. And the emergent term, we're gonna see that like a lot during the course, but like we're talking about things that happen without planning, or without let's say you build a model, you create a simulation, and basically the rules are for the individuals in your model, and the outcome, the macro outcome from the whole population of your simulation is the emergent part of it. So you don't know what's going to happen. Maybe you're going to have like some expected result, but sometimes you just get like surprised by what can come as a result from your simulation, because when you model the individual rules in a micro level, you don't control what's going to happen on your model. So that's kind of what we mean. That's what we mean by emergent. And the feedback loop here, we're going to talk a little bit about that, but it's basically the fact that the macro affects the micro and vice versa. We are going to see some examples in a bit. Okay, so to define even better the term emergency, it's important to even give you some nice examples. So emergency is a concept applicable to situations where a new collective behavior is derived from individual decisions. Holland, the researcher, in his paper in 2014, he said that the action of the whole is more than the sum of the parts. And that's basically what defines emergency, because, as I've said, like you create rules for the individuals in your model, and the outcomes sometimes they are unexpected, and they are like even things that you don't even predict when you're doing your basic research. So it's very interesting how these things can come up. The picture you're seeing like is Rosa Louise Macaulay Parks, and for those who doesn't know this lady, she was an African American activist in the civil rights movement, but she's best known by her pivotal role in the Montgomery bus boycott that happened in the United States during the apartheid period. So, like on December 1st, on 1955, in the state of Alabama, she basically rejected a bus driver order to vacate, to just like stand up and give her seat for white people because she was colored. Um, well, the fact is that during this period in the United States, most of you might know that there was a lot of people unsatisfied with the situation. Even white people or black, and of course, all the black people were upset about the situation, but even some white people were upset with it. Um, but the thing is, after this event, when Rosa refused to stand for other people to sit on her bus, to take her bus seat, the other people who knew her well from church, from other societies, from other groups, from her job, they got so frustrated and so upset and so angry by the fact that she was arrested by just not vacating her seat for white people, that well, that was basically a moment when a very big movement started happening, and other people started like practicing the civil disobedience, which is basically violating the segregation laws. And the movement was growing, 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 up to the point that the apartheid was lifted, and the situation changed drastically. And that's the kind of phenomenon that, well, I don't think Rose was thinking of just like basically ending the apartheid when she refused to get up of her seat. She was possibly in a very angry state, like upset with everything happening on a bad day, and she just like decided like, look, I don't care anymore. Like this is nonsense, and this doesn't make any sense to live like this in a society. And then she triggered like a lot of other actions from other people that would like playing a huge part on the whole civil rights fight for equal rights for black and white people in America. And that's the kind of emergent phenomenon that you can see happening. Like one person decides to not stand, then the other person sees that and decides to not stand as well, then another person decides to not stand, and after a while you have like a considerable like a big group of people following the same behavior, which is going to lead sometimes like to even social change in laws and the way things happen in bigger groups. The other definition we have to talk about is feedback. So feedbacks are the effect of the emergent result on the decisions of the individual. So like as we saw the example of Rose, her individual behavior basically encouraged other people to do the same. And the fact that a big group of people were basically practicing the civil disobedience was also important to encourage other individuals who are not willing to do that without like some social support. So the feedbacks are basically how how let's say how the emergent behavior from the crowd bounce back on the individuals. That's very observable, like in the market. So if you decide to play Xbox, you're gonna buy an Xbox. and the decision to play Xbox is gonna basically affect the shares in the market on the video games. So if you buy an Xbox, you're not buying a PlayStation. So you're favoring Xbox. If after a while, let's say 90% of the people decide to just buy Xboxes, what's gonna happen is that other people will also want to buy Xboxes because you want to play online with your friends, and if your friends have an Xbox, it doesn't make sense for you to buy a PlayStation, let's say. So then the market's basically affecting your decisions because you look to the amount of people who play certain video game, and then you're going to possibly buy the same. It's just how it goes. So this is called feedback, and it's very common to see this kind of stuff when you're modeling agent-based, when you're doing agent-based models as well. So then now we can have a better idea of like what complex systems is. So usually complex systems, they have these three characteristics, like they're difficult to predict, to control, and to manage. They are mostly based on observations from a real life. You see things happening. You try to derive the rules who basically apply to that context. But mostly you don't know well what's going on. Like you wanna investigate it better, and you just basically get your small pieces together and see if you can replicate it on a simulation. Or sometimes you have a huge behavior, um, like a crowd behavior of people doing some nice thing together, and you don't know why they're doing that. Then you try to understand from the micro level. So you try to check like what's going on. But the fact is, when you try to simulate these situations in a computer, they are very difficult to predict and even more difficult to control because mostly you're dealing with like micro rules. You don't have control over everything that happens, like the interactions and the environment, and you have to manage these things as well. So that's how you would like define like complex systems as well. So another topic is like complex systems converge to the goals of public policy, and that's very important to note because most of the work you might develop throughout the course, and most of the work that's done on agent-based models, they are basically investigating stuff who can help public policy. It can be like on a health issues. It can be on safety issues, on urbanism, like a planning of a city's growth and other stuff. So mostly, even the public agencies, they are interested on this kind of research because it helps them a lot to understand how the public money is being spent, and if they even like try to create a new campaign, let's say like they want to create a campaign to make people aware of vaccination and the importance of getting the vaccine. They have to have a way to measure if that campaign is successful or not. And even beforehand, they want to know if there is a chance of the campaign to being successful, and they can use agent-based models basically to build up this knowledge and to have some previous knowledge about what would happen if we like do the campaign like this, if we target these people or if we target those people, or if we just like invest certain amount of money on this specific cluster of the network. So you have like many public policy decisions were made based on agent-based models as well. And of course, like complex systems, because when you are like trying to study society, you don't have like just a couple of variables accounting for the phenomena. You have like dozens of them sometimes. So unemployment can like be a factor that make people decide to become like drug dealers, for instance, or let's say a very nice school, a public school with like a very high quality, can be what defines if that person is going to become a Nobel Prize or not. So and then you don't have like just these simple chains, like the person might have the best education, but the person is not going to become a Nobel Prize because of the home environment, or maybe because that person um, is not like dedicated enough to just like become like a nice researcher. The person just don't care about science, and the person just want to become like a priest, or the person want to become a football player. So in life we have so many aspects that like account for decisions we make, and complex systems are very suitable for this kind of study. That like it's a very challenging way of studying life and studying real life. But what happens that complex systems and digit-based models, they basically provide us with like a nice tool, not a perfect tool, but like a suitable tool that will, let's say, ease our life to study these phenomena. And as I've said, the complex systems, they're not meant to be perfect, but they kind of provide like a flight simulator, as said Holland, like in his article in '96. And when we talk about flight simulator here, like we mean that when you're playing your flight simulator on your computer or on your Xbox, let's say, you have in the simulator all the same controls you would have on that plane. Basically, you can pilot the plane as you would have to do it in real life, but the system is not perfect, in the sense that the weather is not always like exactly the same as you would face if you were like a real pilot, for instance. The conditions of the airplane also, they they are created in your flight simulator, so you can have the best feeling that's like a real like experience. But if you start paying attention to the details, you're going to notice that it's basically not like you can't just do everything with the plane and see what would happen in real life, because of like a physics. They are much more complex than just than what you're able to put in a computer code. So complex systems, they have also these aspects here. Other definition we should define here for you is leverage points, and we've talked about it before when we were studying the fire model. And leverage points, they are also known as tipping points, and they basically uh, define like models and systems where you have in a specific part of it, or in a specific point, in specific settings, that if you adjust your simulation to that settings, instead of degrading, your model is going to start like improving. uh, so it's like it's that moment when, like in the fire model, we started like having just a mild fire spread in the forest, and we started having like a huge fire spread where like the fire was going from one side to another side of the simulation. So places where the complex systems, they can dramatically change the outcome of the whole system, they're called leverage points or tipping points also. And they will provide more information than we expect. Like you can try to find, like for instance, the amount of investments you would have to give to certain society, for instance, in such a way that you can end or at least like and to a big extent the violence, for instance. Like, so how much money would we have to invest in a favela, for instance, to decrease poverty, and in such a way that people quit joining the gangsters, and they start having their own normal lives as everyone else who has like who have like a better socioeconomic condition. So those are like the kind of questions we always want to ask, especially because resources are limited. Like sometimes you just can't invest like infinite money. So you have to decide like how much effort do I need to change the situation in this case here. Okay. The fourth or fifth definition we're going through, I've lost the numbers here, but it's fine. It's path dependency. Dependence. Okay, path dependence. is basically present in the model when the current possibilities are restrained by decisions and choices taken in the past. So that's very common in agent-based models, that like when your agents, they make the decisions, the history of that decision is not going to make a difference in the future. So there are some models, for instance, related to corruption. So if you're like a honest person, and you have to interact with people every day, and you find out that some people are corrupted, you won't make business with those people again. So your experience, like with bribery or something that happened that showed that that person's not trustable, will trigger on your decision making system some new rules for that specific person. So you won't make business with that person anymore. That's how it goes. Like when you're planning cities, like let's say you're the mayor of a big city, and you have some money and you want to invest. You want to invest in the northern part of the city, so that part can thrive and can grow. Or the fact that like you put a lot of money in that part of the city and not in another part of the city will affect the path as well. Like the north is going to be wealthier than the south, for instance, if you don't invest any money in the south, but you invest it all on the north. Like the southern part might become like poorer and more violent, while the northern part is going to become like richer and safer, and that's how things might go. So path dependence is like every model where the decisions you make at certain point will affect the future. The other important term here is sensitivity to initial conditions. So this has some relation with the path decision, of course, but here we are talking more about like the initial values you insert on your model. So I guess everyone have heard of the butterfly effect, and the butterfly effects like something like the butterfly makes like the butterfly like move her wings in Japan, and then you have a hurricane happening, like let's say in Australia or in America, or whatever. So it's a condition of chaos where like a small things like happening in one part of the world will cause like a drastic and big big effect on other place of the world. And agent-based models, it's not all of them, but most of them, they have these characteristics as well. So if you change the starting points, the initial variables just a little bit, this might drag you to a completely different outcome. So every starting point close to another starting point generates a significantly different endpoint. So where do you start in that case matters crucially. And that's what basically defines agent-based models most of the times. The other term here is robustness, and robustness stands for like the systems when the system is able to keep its characteristic behavior even after you change drastically the variables or the way the system works. Like what you're seeing on the background of this slide is the segregation model we've seen last lecture, but like in a more animated way. And for the segregation model, for instance, if you change the thresholds and the sliders in the simulation, you might have like a different outcome. Like you might have more people happy or more people unhappy, but the system is robust enough that it will find an equilibrium, like most of the times when you change. So the system always converge to a position where like people are happy, and that's when the system basically ends, the simulation ends. So robustness is also about like how can your system cope with chains in that case. Um, and last but not least, like there are other terms you're going to see throughout the course, but I don't want to be too long in here. But like we have interconnectedness and social interactions. So when we talk about complex systems, mostly we're talking about interaction, social interaction. So the agents involved in the simulation, They have, of course, they have individual rules, but they also interact with the environment and with each other. And when they interact with each other, that interaction can cause things that we didn't plan before. So the people don't make decisions without getting affected by others, and that's one of basically the things I enjoy studying the most in my research, which is basically social contagion. So like we think we make decisions, but most of our decisions, they are very affected by our environment and other people surrounding us. One example, one very stupid but simple example, is the standing ovation effect. The standing ovation, for those who never heard of it, is like when you go to the theater, for instance, or when you go you go to watch a play, and when you watch a play, by the end of the play, or like an opera or an orchestra, and you have like people standing and clapping after the play is over. What's interesting about this phenomenon, like in a rational world where like people make individual decisions, you'd expect people to have a threshold of how good that experience was. And like if that experience was like better than my threshold, then I would stand and clap. But mostly, what we see is like a lot of people clapping, and sometimes people standing even if they didn't enjoy that much the play. And why is that? Like basically because one of the explanations for that is that when people in front of you, for instance, when people in front of you they stand, there is a social contagion effect that like it might lower your threshold. So like, oh, if the person in front of me thinks that this thing is really really good, then it maybe it's just me that I'm being too picky, so I'm going to stand and clap as well, just to give some moral support to the actors or to the artists who are participating in the play. um, then what happens, it's basically that when you have these plays, especially on the first night when they start the play, they give the best tickets on the first seats for family and friends. And of course, family and friends, they're gonna stand and they're gonna clap and they're gonna applaud the friends and the relatives. And at the front row, when they stand, they basically cause the standing ovation effect. So people behind them are going to start standing and applauding as well. Um, and that happens because people don't make decisions without getting affected by others, and that's like some aspects of complex systems we're going to see throughout the course. So when to use ABM, like talking about these terms gives us a good idea about where can we use agent-based models, but like there are some specific situations where we should or we shouldn't use agent-based models. So the first is like uh, the number of agents you have in your simulation. If you have too few agents and your model is too simple, maybe you could use just game theory or ethnography. You could solve that problem using other methods instead of agent-based model. Like maybe agent-based model is like it's like using a huge gun, a huge weapon just to kill like an ant, as we have this. I don't know if there is this proverb in English, but we have it in Portuguese. Um, so if you have too few agents, the model is too simple. Maybe use another approach. But if you have too many agents, um, and you want to understand more like the statistics of the thing, if you want to get the means and the standard deviation of the variables on that population, maybe just you should just use statistics. Like it's not worth it to create a huge model full of agents requiring big like computational power to just like do something that statistics are fit to do. Okay, so agent-based models basically fit on this category, like a medium number of agents, where the number of agents also affect the outcome of the system. So if you have this kind of situation to simulate, agent-based models like our goal, like just go for that. Another aspect is like heterogeneity. Okay, heterogeneity is basically when your system uh, your system has like a lot of different aspects about the agents and the environment, and just using statistics or equations is not enough to explain everything that's going on that situation. Um, when you usually have like environments who are really rich or social networks, you have a geographical system, so you have a map of a place where that you want to see how people move around that place. um, Systems that have like where agents have like their own agent like rules and stuff like that. Those are like systems where you have like too much variables, and to account for that, agent based models are a very good alternative. um, so agents can be in agent based models, agents can be as heterogeneous as necessary. So if the agent is a person, you want to add the age. Does the age matters? Yeah, okay, we can add the age. The height of the person matters. Okay, so let's just put the height. The income, the salary of the person, does it matter? Yeah, it matters. Okay, let's do it. Just include another variable in there. Well, I want to know if that person is well educated or not. Fine, just create another variable. So you can make the agents as complex and as heterogeneous as you can. And the fact is, like in the same simulation, you can have poor agents, rich agents, tall agents, short agents, white, black, Asian, Caucasian. You can have like all sorts of agents. If it's cars, you can have all sorts of cars. If it's a truck, if it's a car, it's a motorbike, if it's a bicycle, whatever. In such a way that basically you can bring the complexity of the world, like the variability of how reality unfolds to us, to your simulation. And the environment the same. So the environment can be as heterogeneous as necessary. So like if you're building a simulation to try to predict street robbery, for instance, you can define like, oh, this is a this specific spot here in space is it's very dark, or there is a proper illumination, proper lighting in this place. This place is a corner, or no, it's in the middle of the street. There is a shop in front of it, or there is another shop. It's a street for cars. It's a walking path for pedestrians, and so on and so forth. So you can add as much as you want in your model. And if your model is a very heterogeneous, agent-based models is a nice place to be working with it. Another factor that might drag you to agent-based models is local interactions. So local interactions are basically how the agents, uh, if the agents interact with each other and with the environment. So you have like a complex interactions can be as complex as necessary, but they need to be local. So if your interactions, they're not local, if like I don't even have a good example from the top of my head, but the interaction should be local to fit on agent-based models. So you have people interacting with people within your simulation and with the environment within your simulation. They are also history dependent. So previous steps in the simulation, they are going to affect further decisions made. And we've talked a little bit about it when we're talking about the path dependence. But it's important to just say that like if your previous decisions, they don't affect the future decisions, maybe you should rethink the decision of using agent-based models for that kind of a purpose. And they are also property dependent. So the characteristics of the agents will also define the decisions they make. So it's not just about the path, it's about the characteristics of the agents. So when we talk about complex, we're saying that there is no global knowledge in general. Okay, when we say that there is no global knowledge, is I mean like it's like in real life. I don't know what's going on your head or on the head of people who are around me. I just know my own head, and I can read the environment, and that's how it goes. And last but not least, we have basically two aspects here that will be like important factors to decide if you should use agent-based models or not. So the first one is time. So almost all the agent-based models, they have a time scale. Okay, very few exceptions, but most of the agent-based models, the things they happen over time. So you basically count the time, like it can be minutes, it can be hours, it can be days, it can be years, it can be centuries, it can be anything you want. But the fact is, usually we model stuff over time. And adaptation, which is basically another feature that agent-based models have, where agents, they change their decisions based on the past history. And I'm emphasizing this because this is extremely important, and a factor that might define like if agent-based models are really, really, really the right way to go. So as I've gave you the example, like if you're modeling a situation where people interact with corrupted agents, for instance, your agents should be able to adapt, meaning I do business with this guy now, but in the future I'll never do again because this guy is just not trustable. Or I use it to take this path to go home from work. But after I got robbed in here, I'm going to take another way because I don't feel safe anymore walking by this street. So this kind of stuff is very relevant for agent-based models. And yeah, I hope you can apply these things in your models that you're going to build. Any questions up to here? All right. No questions. So we're going to go to the second part of the course. I'm just going to ask you uh, to write your name down on the chat here so I can keep record of who was in the lecture. That's like just for future purposes. Okay, so the second part of the course, and I guess we're going to have to finish this part on Thursday morning. I'm going to confirm because I guess there are some meetings scheduled for Thursday morning, but otherwise we meet next week on Thursday. Is Netlogo. So Netlogo is our tool that we're going to use throughout the course. And Netlogo is it's a programming language, and at the same time it has an interface, and at the same time it provides you with a lot of resources that will make your life easier if you really want to go for agent-based modeling. Um, Netlogo is like a, let's say, extremely flexible on what you can do with it. It has its limits on the number of agents, for instance, you might be able to run. But for learning purposes, and even for like some deep studies and research, it's very suitable, and many people have been using it for a long time. So I'm gonna start like I'm just gonna open here our fire model. So we've seen this model last lecture. I want to go back to it just to show you some of the elements present in here. And just to start, I want to point out that Netlogo has basically three tabs. Okay, so the tab we've seen so far is the interface tab. You can see here that there is an interface tab where basically we have this black box here, some buttons, some slider, and stuff. Okay, We've seen like how it goes. You click setup, you click go, things happen. You change the slider, you click setup again, you click go, things happen, so on and so forth. But like what I'm going to start today from the tab in the middle here. So that's the info tab. And this is the first difference from a Netlogo to other languages. Most languages, they basically have the documentation inside their own code. Like sometimes you just create a header, a huge header, where you explain what does the code do and what's the purpose of that program and stuff. Or sometimes you create a README document separated where you kind of give an idea to the people who are going to use your code about what does it do and how do you use it and what do you expect when running this code. On Netlogo, you have a specific tab just for that. So here on the info tab, you're going to have basically the whole description and the documentation of your model. And that's very interesting because it's not just about talking about the code, like on this line, I did this or I did that. Um, it's a full description of the model, the assumptions you made when you built the model, how can you extend the model, how can people explore like your model, like what you even like you can even suggest some specific things that people can do just to learn from your model, some related models that you might be based on the credits, how to cite. So that's very important, especially for scientists, because when you basically when you build a model and you put the code available, it's super nice if people can cite your code in their paper, because that basically brings the visibility to your work. And you even have like copyright and license guidelines here, so people can know if you are okay with sharing that thing or not, and so on and so forth. So the info tab is basically the place inside Netlogo where you're gonna inform the people who are gonna use your code later about how it works, what it is, how to use it, and so on and so forth. So on the info tab, basically we have only two buttons. So we have a button of find. So if you want to find some term in there, like let's say I want to find the term fire, so then it's just gonna basically show me where the word fire is on my simulation here. It's not highlighting, but that's basically what it does. Like oh yeah, it's highlighting here, like fire here, and then fire here. So it's like just a search button. It's nothing major. And the other button is the edit button. And here it's important for us to understand how it goes. Because when you click on the edit button, then the info tab becomes like a text editor for you to write down your code. So I can even change here what people have done. Like so I can write down here. So you can change the document here, for instance. And one important thing to say here is that Netlogo uses Markdown. And Markdown is kind of a programming language for text, very simple one, where basically you use like hashtags here, like for creating titles and subtitles, and you basically write down stuff. If you want to create a list, you have like the way to create a list or a web link or italic, bold font, and so on and so forth. So it tries to keep it simple. So you just you worry more about writing down what you need to write down, but at the same time, it formats the text for you. So when you get out of the edit, it looks beautiful. It looks pretty, and it's aesthetically attractive. And as you've seen, when you click on edit, a third button shows up here. This button basically opens the help website for the info tab on Netlogo documentation, where here you basically have some idea about how to do some headings, some paragraphs, italic and bold text, how to create ordered lists, unordered lists, links, and so on and so forth. So you can even like always go to the documentation webpage to um, to learn how to do stuff using the markdown. So that's the info tab. Okay, the code tab is where basically the program happens. So that's the code. The language here, you might like don't be scared at first. Like it's a programming language as any other language, as Python is or Java is. Of course, it's a different paradigm of language, but we're going to go through the code and how we're going to learn how to build the code and how to read the codes and to create loops and to create lists and conditional commands and stuff. But like basically the code tab is where like it's like a under the scenes part of the model where things happen and where decisions are made. So when you go to the interface, you don't have to bother seeing all those codes. You just see the beautiful part of it. It's like the front end and the back end. And the interface and the code, they are connected, of course. Like things that you build on the interface, they become variables for the code. And if you create something on the code, you can create later some buttons or anything in on the interface using variables that you've created on the code as well. But let's focus on the interface today. And then in the next lecture, we are gonna start learning how to code. Though you have homework already to do at the Campus Virtual at our website. So don't wait too much. Just go there. Take Jennifer Badhan's tutorial and read and do the exercises and go through the codes and everything. If you have any questions, use the forum. We have a forum for that. So don't wait too much, because like it's gonna make a huge difference if you start like studying now. So then we go back to the interface tab, and we have the interface tab as we've seen, and we have like a couple of elements here who are important to note. Okay, so we have here on this white square in the center here, that's basically the place where you build stuff. You build like your buttons, your world, your monitors, and everything you need to follow up with the code you've created. In this case here, we have basically three different elements and the world. So this square in here, like this square in here is called the world. And it's where everything happens in there. Usually it's squared, but you can even work around that later. We're going to show how it goes, but it's a squared world. And it's where basically your agents will live in. You're going to create the environment, you're going to put the agents in there, and from that point, they're going to do what they have to do. Setup and go are two buttons, so those are buttons that you can also create. This is called a slider. So this slider here, it's a density slider, and when we move the slider, we're basically changing the density. So if I reduce the density here a lot, like to let's say 23%, you're gonna see that the trees are much less present in the forest, and they're more sparse than if like the density is 88%, for instance. So that's basically a variable represented by a slider, and this is a monitor. So like the percentage, the percent burned part, the part of the forest which is burned shows up here. It's a monitor. Okay, so here usually we show some variable, or we just code what we want to show in here. And it basically shows like as the forest gets burned and burned, shows the percentage of it, which is burned up to that moment. So if I stop the go now here, like then that's the time schedule here, the time dimension in our model. You're going to see that at this time step, it's 78.3% of the forest burned. Well, I can add more stuff in here. So here, when I click, I have all the elements I can create. So as we've seen, I can create a new button in here, and this button can be, let's say, it's gonna be my setup, okay? And on my setup, I'm just gonna say setup and go once. Let's see what happens here. And then when I click on my setup, it creates the setup and go once. So I created my own button. I can go here and edit it and just like code and put as many commands as I want here. And that's how basically it goes. It has some characteristics. We're going to talk about the agents, the I forgot the name of that now, but like the agent can be an observer, it can be a turtle, a patch, or a link. We're going to go through this later. It's not important now. Our button can run forever. So if you click in here, it's going to run forever, meaning that it's going to repeat this command over and over and over again. And we can even disable the button until the tick starts. We're going to talk about the tick in a bit as well. I can create a slider. So we had one slider ready, but we can create another slider. So I go here, slider, and I click on the space where I want to build this slider. And when we open the slider window here, you can see that you might create a global variable name for it. So this slider can be just a test slider. I'm not worried about anything here. You can see that it has some variables. So the minimum value for this slider is 0, the maximum is 100, and you can increment it one by one. That's basically what it says. And the value, the initial value is 50. So the slider starts in the middle, like on the 50. And you can even choose unity. So it can be like centimeters, for instance, and I can even make it vertical or horizontal. It's up to you to do it. So when you create, you see that the slider has a name, it's test slider. And if I change here, I change the number of centimeters, for instance. This slider could be like the distance between the trees, the minimum distance between the trees I want to include in the model. And then when you build the forest, you force the trees to be distant from each other, at least at like 28 centimeters, for instance. It's like a very small number, but you got the idea. We have switches, so I'm going to put it on the other side here, just so you can see that we can put it anywhere in this white space. Switches are like Boolean variables, where they are going to become global Boolean variables that can assume a true or false values as their equivalent. And they usually, like you can create here, like let's say age. Let's say like I want to create a variable that's called age. And the Boolean variables in Netlogo, they have this interrogation mark in front of them. It's part of the language, and you should use it as well. And in this case here, let's say this is a button that, like, if I turn it on, then that means that my simulation is gonna account for the fire brigade, providing some aid to put off the fire, for instance. Okay, and if it's off, we don't have the aid. It's something like that. We have also choosers, and chooser is like it's a variable where you predefine the options that the variable can assume. So I can, let's say I wanna create a global variable that's gonna be the weather. So let's say it's rainy, or it's like a windy, or it's snowy, or it's sunny, for instance. So let's just say like we have these 4 possible weather variables, let's say. So that means that like you can come here and basically pick which kind of weather you have at your simulation. And of course, like if it's windy, the fire might spread more. If it's raining, the fire might spread less. And the other variables, like you'd have to create rules for them. The other possible element you can add here is the input. So inputs are just like inputs indeed. Like so, I can create here like a, let's say, number fire brigade guys. Let's say like a, and I want this to be a number. So like I wanna tell them like that I want 10 fire brigade guys helping to put off the fire, and then my simulation is gonna run and it's gonna read this variable and use it. So it's like an input. So it's like you are like um, providing information for the code. We have monitors. So we've seen one monitor in here. We can put another one. So these monitors, they basically show the result of something you want to show. So I want to know, like, let's say I want to count the number of trees who are funnily called turtles. We're going to know why in a bit, like maybe next week. But let's say here, like a number of trees, for instance. I want to know how many trees do I have in my model. So it shows here we have 432 trees in this model here. If I reduce the density here and I do a setup, oh, now it's 251, so we have less trees. But what if I have 99% of the density? Well, then it should show here more than that. Let's just see if it's gonna, well, I don't know why. It's oh no, but it might be like a number of trees. Yeah, and it's the number of trees that were burned. Basically, that it is counting. And in this case here, you put fire on like almost 3,000 of trees so far, and by the end of the whole simulation, you have like 0 trees left. Interesting. Yeah, it goes up and then it goes down. So that's the monitor. We can plot stuff. So we can have graphics during the simulation, so you can see things happening during the simulation. In this case here, we are counting the number of trees over time. So let me put here trees. Let's just see what happens in here. So if you do a setup and go, you see that there is a graphic showing like the variation on the number of trees in the simulation, for instance, and then like a down. I'm not gonna go through like how it works perfectly, but just so you can have an idea what we can use to build the simulation. We have output, and these outputs here, they are usually just text. Okay, they usually just you kind of you use these outputs just to show some message to the user of your code. And last but not least, you have notes. Okay, and notes are just a nice way to organize your environment here. So you can say like I have an area just for graphics, for instance. I want this area to be red, the color of it, and I want the font size to be 20, for instance. Let's say here. Then it's gonna create a label. It's like a label you just put here. It doesn't do anything. It's not like a part of the code. It's just aesthetics of your interface here. Okay, so those are basically all the elements you can add. The world here, you have only one. You can't add another world, and things are going to happen in here. That's basically where things go. We have this slider here. Okay, this slider here basically defines how fast you want to run your simulation. So let's say I want to run the simulation here, but I want it to go slower. So I move the slider here. And as you can see, there are some ticks, like the ticks here, like your clock. So you count like the time step. So like time step 60, 61, 62, and every time the tick is incremented, you can see that the simulation moves a little bit. Okay. Oh no, I want to go faster. So be fine, you go faster. It's okay. If I want to go slower, you go slower. The thing is, the faster you go, um, the least you're going to see of the simulation. If it's not important for you to see the simulation in the world happening, if you're more worried about the numbers, you just go as fast as you can. If it's important for you to observe what's going on, you just go slower. The ticks are your count or your time count. So we're gonna go through that as well, but that's basically your clock. Okay, so your simulation usually starts on tick zero, and every time you move one time step, your tick goes up one. Davi, do you have a question?
I have a question. This tick would be a pass of in the iteration, or I can change how much time it has passed. For example, during the game of life, I think one tick was one iteration of the game. I can change to count like 5 iterations and then change it drastically, or is
Well, the tick is the, how can I put it? The tick is the minimal time schedule you have in your models. Like so, like for the game of life, it doesn't make sense to go 5 by 5 because the interactions between the 1 and the 5 they're important and they define like how do you get to the 5. But the ticks they're generic as well. So in this case here in our simulation, like they don't mean like a specific amount of time, but they can mean, it can mean like you can make a model where one tick is 1 second of a real life event, or one tick is 1 minute of a real life event, and you want to count time as in real life. You can do that. If your model is like the game of life, or like this example of the forest, or like the predation, the predator simulation we've seen last lecture, then the ticks are just time steps. They mean like they basically separate the state of the simulation now from the next set of interactions that will happen between agents and the environment. Okay, that clear?
yes, thank you.
Yep. So there we go, have ticks. You can also decide to not see the updates, okay? It happens sometimes. So I can come here, I can deactivate the view updates, and when I go, things are gonna happen, but I won't see anything on the in the world here. And when I see, it's done. Why would I do that? It's basically, well, the thing is, after you've tested your model and you know that your model is working fine, you want it to run fast because you're gonna possibly have to run your models hundreds, if not thousands of times to get to the results, because you have to calculate the average. Your models are always stochastic, so you need to run them many times. And when you view the updates, when you enable the view activates checkbox, it basically delays your simulation because the Netlogo is gonna take time to run your code, but it also has to take time to build the graphics of your world. So usually when you want to do your simulation fast, you just disable it. It's okay. And here you can even decide like if you want to view your updates on ticks or in a continuous way. Okay, we're going to go through this later. Don't worry about it now, but this is just basically the rule for when to update your simulation. We're gonna see later how it goes. We have also a button of settings here, and the settings, it's the same as if you click in the world and click on edit. It's going to open basically the same thing. It's your model settings. And here we have some important things to show you. So first thing is like you can change the size of the world, okay? You can define how do you want the coordinate systems to work. So for instance here, like what's this area here for the world, it's basically showing that the origin like of your matrix, that's basically a world, it starts at the center. So that means that the 0, 0 coordinate is at the center of your world. We're going to see why is that important later, but like when you build your agents, you have to give them the location where they are built. And the locations are like coordinates, like x and y coordinates, latitude and longitude coordinates and stuff. And here it's basically saying that the 0, 0 is in the center. I could put it in the corner and decide it's the bottom left, so it's here now. I can say, no, I want it to be on the top right, so it's here now, it's also fine. I can decide that it's in the edge, so then it's here, it's in the middle of the edge here, 0, 0, and so on and so forth. Like mostly we just put it at the center. You can even customize it and decide like where do you want to put the origin, okay? And in that case, you basically put the coordinates here. So I want it to start on -10 and plus 20. So then it's going to start at that point, okay? But let's just keep it at the center. And here I can decide the size of my world. So I can just like change here. Instead of 125, I want to have a world at size 50 and 50 by 50, for instance. And when I apply here, you're going to see that my world here is much smaller now. And it keep, like if I click OK in here, and it keep working. It works the same, okay? Like it's gonna still function the same way, but my world now is smaller, okay? It's a 50 by 50 world and not a 125 by 125 anymore. You have two checkboxes in here to wrap the world horizontally and vertically. And I don't think this is a good example. This is not a good model to show you how does it work, but I'm gonna, so let's go to the flocking model here, then you will understand it better. So the flocking model, as you remember, is that model with the birds. So we have birds flying and following those three rules for heading towards the group, not like not bumping in each other, and changing the orientation based on their local neighbors, and then they create a flock. They create like the Starling's murmuration phenomenon in here. Okay, if I come here and go to the settings, in this case here, we have the same thing. We have the world with the center is the location of origin. It's a 35 by 35 world. And check that these two boxes here, they're checked, meaning that basically if the birds, they fly and they hit one side of the world, they end up on the other side of the world. So it's like if the world was wrapped around, and horizontally is like means that the world's like this, and the vertically means that the world's like that. I don't know how to explain that. I think you got the idea. So what happens that if I come to this simulation here and I uncheck these two boxes, just notice that the edges of the square here, they get red. The first thing, they become red. Meaning it's not a free area anymore. They can't just like fly through. They are gonna have a wall. It's like a wall in there. So if I do that and I keep running my simulation, what happens that the birds are gonna get stuck in the edges because the world's not wrapped around anymore. You see that? So now the birds, they're like they don't fly through one side and get on the other side. They just get stuck in that area there. So that's basically what it does. This checkbox here, it wraps the world around. So if I release them here and I apply, check it out, the birds go back flying normally. So if they go in one direction and the limit of the world is over, they just go through and end up on the other side of the world. In the view part here, you have some some view options, of course, but like you have the patch size, so you basically define how many pixels each patch, and each patch is it's like each minimal area of your space in your world. We're gonna see that later as well. And the font size for agents labels, and the frame rate. So this is a simulation, a dynamic simulation, and it defines basically how many frames per second it shows. So if you want to record the simulation to show someone or to publish your paper, you can do that. And here you have the tick counter. So you can show or not your tick counter. And you can even change the name of the tick counter. So instead of ticks, now I have hours, for instance. Let's say here, let's hours, and it's going to become hours. And as you're going to see here, it changed the name from ticks to hours. So every time you talk about ticks, it's not ticks anymore, it's hours. It could be minutes, seconds, time step, anything you want. Okay. And that's basically uh, everything in the interface on the upper part. We also have the command center below here. I'm going to stop the simulation. And the command center is basically a place where you can uh, type commands and see the results. So here you can even do some maths. It's going to show the results. It's like a terminal for Netlogo, and it's very well used for testing your code, for debugging your code. After your code's done, rarely you're going to use the command center, but it's nice if you want to test a function. Instead of going back all the time to the code and checking, you can just type it here. Like so I can, for instance, ask all turtles to set their colors to blue, for instance, and that they're going to all become blue. Okay, it's just one command you give here, and it has an effect in there. I can ask all turtles to, let's say here, to move. No, I'm not going to do that now. It's going to be too complicated. But like, I can, let's see here, to set their size to 3, and then they're going to become bigger, for instance. Okay? So you can do many things with the command center. We're going to see a lot of them from the next lecture on. And yeah, that's basically Netlogo. That's the interface, the tabs, the elements of each tab. And next lecture, I hope that we go through the coding part, which is the most difficult part, of course, but it's also the most exciting part, because then you can start doing nice stuff with Netlogo. Any questions, guys?
I have a question. Um, I, at my final project, I'd like to generate some simulated data to my master thesis. I like to generate financial data. It's more like a transactional data to perform a money laundering detection. And I would like to generate data based on agent-based modeling, using agent-based modeling. And I'd like to see some models to follow the idea. Where can I find them?
The first place you should look for this kind of stuff is on the models library, okay? So when you open Netlogo, if you go on File, you have Models Library. And on Models Library, you have tons of models built by other people, of course, but like models that work, and from where you can even copy and paste some code. You can get some ideas. You can use as the base for your model you're gonna build. And like let's see, I don't know if there is a money laundry things here, but it has some stuff on economy for sure. So you have like a bank reserves, this model here, creation of money in an economy through a private bank system. So there is one model. Cash flow, It's an extension of the bank reserves. Help the user examine whether there is a relationship between the reserve ratio that banks must keep and stuff. Investments hubnet, so you have like some investment stuff in here that might be useful for you to do the the money laundry, because of course you're going to have some relationships that needs to be kept to build the chain of the money laundry stuff. Simple economy. Let's see here. We have some corruption stuff. Let me see if we have. No, we don't. But like you can search. Like if you go here in let's say social sciences here, you're gonna find a lot of stuff. So you have like models for altruism, cooperation. Within economic, you have like a Hotelling law, binding market, Brez paradox, and so on and so forth. Like rebellion, like you have rebellion stuff in here, like how to know if like the population is gonna rebel against the authority or not, based on how satisfied they are with the government or not. Um, the segregation model, we've seen it before. So the thing is, you should look for similar works first in literature, and I'm sure there are some works on agent-based modeling and laundering money, because I've possibly seen them. But yeah, if you need some help, just let me know. But every model you start, like just go to the libraries first, check if there is something similar. And sometimes it's not even the same context. Sometimes you find a model from physics that describes the same phenomenon you're studying on social sciences, for instance. Or there is some biological model of like ecology and the populations, and but like the rules from that context, they're the same rules that apply for your like social simulation. So it happens sometimes that you cross uh, some uh, some fields to get to your model in there.
Okay, thanks. And how is the best way to share our model? Because it generates a Netlogo file, and how can I show this Netlogo file at something like GitHub or other one?
Yeah, you can use GitHub. The Netlogo is just one file. Everything you do in here, it's going to become one file. Your code, the interface, everything, it's going to become a text file on the language of Netlogo. So when you open it again, it puts the buttons on the same place, and the word and the code's there. So the thing is, Netlogo, but just by sharing the Netlogo code, you basically share everything, unless your model like has like data from outside. So if you need to import data, of course you have to provide the data as well. You can always upload your model to Modeling Commons. So they have a website called Modeling Commons, where you have like a database of models that everyone who works with Netlogo and agent-based models, they provide the codes in there. So it's even more than the library. The library is more restricted to the approved codes by the team, but you can create an account, you can go there. There is a website for that. But mostly, what I do usually is like when I publish my paper, I make sure I have a permanent link where people can just go there and download my code, and that's it. Like just make sure that the info tab is very well written with all the descriptions people need to, just not to replicate your model, but to evaluate and even criticize, because that's important. Sometimes you have some flaws in your model, and um, it's like you get so attached to your model that you stop seeing the flaws, and other people should be able to see them. And a good info tab will surely help a lot other people to be guided throughout your code, and to find like some weaknesses and stuff.
Okay, thanks.
Yep. Thanks for the question. Very good questions. Anyone else? Nope. All right. So that's it for lecture 2. I hope to see you on lecture lecture 3, which I will confirm. It might be on Thursday morning, but I'm not sure because I have the feeling that there is a meeting scheduled, like from the university staff. So I will confirm. You're gonna get an email saying if it's on Thursday or not. Next Tuesday is a holiday in Brazil, so I hope you enjoy the holidays. And that's why I stretched a little bit the homework too. So the homework too is for 2 weeks, as you've seen in Campus Virtual, but it's longer as well. It's enough work for 2 weeks. So the sooner you start, the better. I just want to emphasize that again, so you can start it the sooner you can. And that's it, basically. Stop